off, change layout. I've never seen this. Okay, so Winona Henline is recording. So Winona, if you could share this with me, the recording, after class, I will post it. But for some reason, I'm having some kind of technical issue. All right, there we go. So somebody's recording. Perfect. Thank you, you guys. All right. Organic chemistry students to the rescue. Okay, well, let's get started. And we're going to start by reviewing a bunch of the reactions that you learned last semester, whether it was last spring or over the summer. Okay. Check one thing, and then we'll get rocking here. Here we go. Okay, Chemistry 3111, Chapter 11, Synthesis. Most of the reactions that you learned last semester involved one step, right? They just involved one reagent or a solvent maybe on an arrow. Every once in a while you learned a reaction that involved two steps, like say ozonolysis is ozone followed by DMS. But virtually everything that we learned was a one-step synthesis, if you will. And that's, our reactions that we've learned. So solving a synthesis problem or providing the reagents is straightforward when only one reaction is needed. And here you can see we start with an alkene, right? We have an alkene here in our molecule, and then we're making this vicinal dibromide. And the way that we would do that is simply by adding bromine to the molecule. And so, oops, didn't need to do that. There we go. So let me just erase this, and then I'll say, okay, all we would need to do this reaction is nothing but Br2, right? We just need bromine to do that. You have to master all of the reactions that you would have learned in Organic Chemistry 1 before tackling the multi-step synthesis problems that we're going to look at in this chapter, and before, moving forward in Organic Chemistry 2. So you really have to master all of those reactions. And let's start here with this slide, which is a question straight out of our textbook, straight out of David Klein's 3rd edition of Organic Chemistry. It says, identify reagents that can be used to accomplish each of the transformations shown below. If you're having trouble, the reagents for these transformations appear in the review of the reactions at the end of Chapter 8. And so Chapter 8 deals with the chemistry of alkenes. It's all alkene chemistry. And so if you're rusty on these reactions, or if you've forgotten some of them, it might be a good idea to go back and review Chapter 8. So let's start right here. Why don't we start right here? And you can see that I'm taking this alkene, which is 1-methylcyclohexene, and I'm adding bromine to that. And where that blue arrow is, can somebody tell me, is that bromine being added in a Markovnikov fashion or an anti-Markovnikov fashion? Or is the addition of Hbr, I should say, it's anti-Markovnikov, right? Yeah, this is an anti-Markovnikov addition. And so the way that we do an anti-Markovnikov addition is by using Hbr, but we also need an organic peroxide, which we abbreviate ROOR. Great, thanks a lot, you guys, for the answers. That's awesome. So that's a Markovnikov addition of Hbr across that double bond. The next one, now we're going to go clockwise. The next one is a Markovnikov addition of Hbr, and for that we simply use Hbr, right? We just use hydrogen bromide, and that will affect a Markovnikov addition, and you should be able to draw that mechanism. In Chapter 10, we spent a lot of time looking at the anti-Markovnikov addition, and so you should understand both of those mechanisms and be able to draw those. The next one, you can see that I'm cleaving the double bond, right? I'm breaking that double bond, and I'm making this new compound that has both a ketone and an aldehyde in that, and the reagents that we would use for that are ozone, because this is an ozonolysis reaction, and it's two steps. The first step is that we treat the molecule with ozone, and for that we use an ozonizer, or an ozone generator. And then in the second step we use DMS. Does anybody remember what DMS stands for? Wrapper. That's DMX. Dimethyl sulfide, yeah. DMS, so if we put up here, DMS is dimethyl sulfide, which is this, yeah. Dimethyl sulfide is an extremely stinky compound, just smells terrible. If you ever spill DMS, everyone will know, okay? So you also might remember that David Klein, sometimes he'll kind of throw different reagents at you. And besides using DMS, you can also use zinc and water. But I think that's only mentioned maybe once in the entire book. But anyhow, it's a good idea to have that under your hat. The next reaction is one which is a syn dihydroxylation of an alkene. We looked at, I think, I wrote it down last night. I was making some notes before class, We learned 5 different ways to do this. And you're like, what? 5 different ways? Do I have to know 5 different ways? No. Okay. The one that is used most often in our textbook is a catalytic amount of osmium tetroxide and NMO. And NMO stands for N-methylmorpholine N-oxide. So an N-oxide is a functional group that we don't really study in detail in Organic Chemistry 1 or Organic Chemistry 2, but you should have an idea what it looks like. So catalytic osmium tetroxide. And the reason why a catalytic amount of osmium tetroxide is so attractive to an organic chemist is because osmium tetroxide is extremely toxic. So that is a syn dihydroxylation. The next one is an anti-dihydroxylation. And I got some good news. There's only one way that we learned how to do that. And the way that we learned how to do that was in the first step was to use a peroxy acid. You might remember a carboxylic acid is abbreviated like this. If I have a peroxy acid, I have an extra oxygen like this. So a peroxy acid, which looks, if we draw the Lewis structure out, it's going to look like this. We have 2 oxygens like that. Anyhow, so a peroxy acid, and the peroxy acid that is usually used in our textbook is MCPBA. So MCPBA, which stands for metachloroperbenzoic acid. And we could, even draw the structure of it out here, metachloroperbenzoic acid, which is this compound right here. So this is MCPBA. And what that does is it makes an epoxide, right? So you should know what an epoxide is. And then we blow that epoxide open to make the transdiol using a catalytic amount of acid. We'll just write H3O+. Let's see. The next one is adding bromine and a hydroxyl. So this is a halohydrin formation. And the way that we do that is we treat the molecule with bromine. And for a solvent, we use water. And water comes in as a nucleophile, and it attacks the bromonium ion to give us an anti-addition so that we get the hydroxyl and the bromine being trans to each other. There we go. All right, I'm lecturing and I'm realizing that I should have done this in the PDF format instead of what's this called, PowerPoint. But anyhow, we'll figure it out. All right, anyhow, the next one is just a simple bromination. So just a bromination. So for that, we just simply use bromine. This summer, I think it was David who asked me an excellent question. He just said, what's the solvent? Is there a solvent, or do you just throw, pure bromine at a molecule? And the answer is absolutely. You would normally use a solvent, but in our textbook, oftentimes solvents are left out, okay? And you don't have to really stress about that. If they're left out, it's okay. Anyhow, there we go. So the next one is a hydrogenation. I cannot move my screen up a tad. No, I can't, because I'm presenting from PowerPoint right now. So PowerPoint takes up the entire screen. I'm in presenter mode. Anyhow, the next one is a hydrogenation. And for that, you simply need hydrogen and a metal catalyst. It could be palladium, platinum, or nickel. We'll just choose palladium for fun. The next one, I'd like to ask you guys about this next reaction. I'll use the blue pen again. Is this a Markovnikov or an anti-Markovnikov addition of water across this double bond? Is that Markovnikov or anti-Markovnikov? Yeah, Diego says it's anti, so does Skylar, so does David. Well, 3 people say it's got to be true, right? It's just like the internet. Absolutely. So that's an anti-Markovnikov addition. And the way that we do that is first by treating the molecule with borane and THF. And then in the second step, we treat it with hydrogen peroxide and sodium hydroxide. There we go. So that's anti-Markovnikov. I'm not going to spend a lot of time on the next one because it's simply a Markovnikov addition. of water across a double bond. So we'll use H3O plus to do that. All right, let's start over here, right here with this methyl cyclohexane. In order to brominate that, we simply treat the molecule with bromine, so just Br2. But what else do we need? Can anybody tell me what else I need besides just bromine? There's something else that I'm missing here. UV light. I like the way you think. Yeah, so we need electromagnetic radiation, so we'll just put H nu, which represents our light. And then we have one more. I'll pick a different color here for the last one. The last one, we're doing an elimination reaction. Can somebody tell me, I'm going to use a green pen here. When I do this elimination, this is an E2 reaction. Am I making the Hoffman product or the Zaitsev product? Can anybody tell me, is this the Hoffman product or the Zaitsev product? Yeah, exactly. Thanks, Sabrina. That's the Zaitsev product. That's right. And so in order to do that, we're going to use an unhindered base, right? We have a tertiary alkyl halide, and we want to get exclusively the Zaitsev product. And so we're going to use something like sodium ethoxide, right? If I was to take that tertiary alkyl halide and I treated it with potassium Tbutoxide, okay, in that case, I would get this molecule, which is methylene cyclohexane, right? So this would be the Zaitsev, the one with sodium ethoxide, and the one with potassium Tbutoxide. That would be the Hoffman product. All right, so that covers virtually every reaction that you would have learned in Chapter 8. In fact, we've covered almost half of the content for this chapter already, right? Because it's just a review. And mainly what we review is Chapter 8 and Chapter 9. So let's move over to question 11.2. This is another good one. It helps us to review, or forces us to review, all of the reactions that we learned where? In Chapter 9. So this is Chapter 9 chemistry. Get out the blue pen here. Where should we start? We have methyl acetylene, or you can call this propyne, right? This molecule, propyne or methyl acetylene. Either way, it's fine. Let's start with this reaction. We're adding HBr across the molecule, and it's being added in a Markovnikov fashion. So for that, we're just going to use HBr. And if you want to write one equivalent, you can do that. Since you're only adding one molecule of HBr, that's totally fine. If you didn't write one equivalent, I would, probably accept that as being fine. But it's always nice to understand, like, what the heck is going on here, right? You have to understand stoichiometry, and that we're reacting one molecule of this with one molecule of HBr. All right, let me clear that. Yeah. Okay, so the next reaction, let's take a look at this one here. We're adding a second molecule of HBr. So for that, we're just going to use HBr. I want to address this one right here. Okay, if I want to take this geminal dibromide, okay, so this geminal dibromide, I'll circle it in green. If I want to take that and convert it to the alkyne, I'm curious if anybody out there in Microsoft Teams land, if any of my wonderful students could tell me how the heck to do that. You can unmute your mic, you can type it, anything is fine with this guy. All right. Okay, so David wrote sodium amide. Excess. That's right. Absolutely. So we need excess sodium amide. Correct. Let me delete that first. Delete my funny looking green circle here. Oops. I lost my HBr in the process. I'll fix it. There we go. Okay. So grab my green pen. Right. So first step, we need excess sodium amide. Right? And in the second step, we're going to throw water on it, right? To protonate it. Absolutely. The same thing applies to this reaction here, right? Remember, the relationship between these two bromines is that they are geminal. The relationship between these two bromines is that they are vicinal. Okay? But either way, the reaction is the same. We would use an excess of sodium amide, and then we would throw water on it, like that. There you have it, folks. Okay, let's take a look at another one. We're kind of bouncing all around here, aren't we? Why don't we do this one down here? Could anybody tell me how to do this transformation here? Excuse me. Did anybody tell me how to do this transformation? Take propine and make a carboxylic acid and carbon dioxide. All right, so yes, thank you, Skylar. Excellent. So Skylar says in the first step, you're going to treat it with ozone, and in the second step, you're going to treat it with water, right? This is an ozonolysis reaction, right? And since this is a terminal alkyne, meaning an alkyne that has a hydrogen attached to one of the sp hybridized carbons, we use ozone, and then we follow that by water. Let's go back up to the top here. Let me grab the red pen, and we'll go up here. Okay, and I'm going to go over these ones for you because these ones students tend to maybe forget these sometimes. So this first one that I have the red arrow here, this is the result of a Markovnikov addition of water. And you're like, hey, I don't see a hydroxyl. How did you add water? Well, when you treat a terminal alkyne with sulfuric acid, mercuric sulfate, which is HgSO4, which is mercury 2 sulfate, in water, you end up forming a methyl ketone, right? This is a methyl ketone, right? Because it's a ketone and you have a methyl group attached to it, okay? Where did that methyl ketone come from? It came from an enol. So if you have to review, you should know that that came from an enol. And I will draw the enol. Okay, it came from, sorry, fix it up so it's consistent with the way I have it drawn. There we go. So it comes from this enol, which looks something like this. Okay, and then the enol will undergo tautomerization to produce the methyl ketone. Now, obviously, the enol comes first, and then the methyl ketone comes second. But I'm just drawing it there because, hey, it's our first day back. I just want to jog your memory, so I'm helping you remember some things here. Let's look at the next one. The next one is the result of an anti-Markovnikov addition of water. And the way that we do that is to use 9-BBN. Okay, and there are several other reagents that you can use in place of 9-BBN. You could use R2BH, that works as well. Dicyamylborane will work, but 9-BBN is usually the one my students like the most. And then in the second step, you treat that with hydrogen peroxide and sodium hydroxide. Again, this aldehyde, right? This is an aldehyde. Aldehyde is the result of, or is the result of the tautomerization of this enol, okay? Because what you're doing is an anti-Markovnikov addition of water across that triple bond, okay? So again, if you don't remember that or you're rusty on it, make sure you take a look at that. I'm going to ask my students about the next reaction, which is one of my favorites because it's one of the few times in Organic Chemistry 1 where we learn to make a carbon-carbon bond. You can see the starting material has 3 carbons, but the final product here has 4 carbons in it. Could anybody, just kind of give me an idea how I might do this transformation?
You could start by the sodium amide.
Heck yeah. I like the way you think. Sodium amide, right? That will affect the deprotonation. And then what do I need to do? I'm adding 1 carbon to the molecule.
So you're adding CH3I?
Yes, so methyl iodide, right? Yeah. Or iodomethane. Absolutely, yes. This summer, I explained to my students, I said, well, methyl iodide, thank you. Methyl iodide is a great reagent. It's expensive, but if you're only on a small scale, hey, go for it. Break the bank, right? What's next? We're taking this alkyne and we're doing some hydrogenation reactions. Here, if you want to make a cis alkene, the way that we do that is we use hydrogen and Lindlar's catalyst. So Lindlar's catalyst. If you look at the ACS study guide, instead of saying Lindlar's catalyst, sometimes it'll just say poison catalyst. It's the same thing. It doesn't matter. The next one is taking the alkyne and completely hydrogenating it. For that, you just use hydrogen and palladium, platinum, or nickel. Let's try platinum, high rollers. And the next one, hey, I'll ask you guys. Does anybody know how to make a transalkene from an alkyne? Anybody remember this one? Excuse me. What does Aaron say? Ah, beautiful. I love it. Excellent. It's sodium. That's right. And liquid ammonia. Absolutely. Absolutely. Yeah. Great reaction, huh? I'm not the kind of guy that likes to mess around with sodium, but hey, if you got to, you got to. Anyhow, where are we now? Okay, we got two reactions left. The first one is this one here. I'll use the red pen. But this one here is you're just adding one equivalent of bromine, Br2, across the molecule. So what I would write here is I would write Br2, and then I would put one equivalent. I'm really obsessed with stoichiometry. And then for the next one, since you're adding two molecules of bromine, I would put bromine, and then I would just write excess like this. Or if you just want to write excess Br2, that works for me as well. Okay, give me a thumbs up if you remember every single reaction that we looked at in question 11.1 and 11.2. You spent the whole summer, woke up every morning with bated breath, couldn't wait to get into the organic chemistry. All right, one person. Okay. Anybody else? You know it. All right. I love it. That's fantastic, Sean. Good. Excellent. I think one of the last thoughts I left you guys with was, it's a good idea to review these reactions over the summer, maybe every day or every other day, take a look at them, because every single person that's online right now, I don't know everybody that's online right now, but I know that each one of you spent some serious time learning these reactions, right? You must have, or you wouldn't be here, okay? So protect that investment. And again, if you're a little bit rusty, try to jog your memory and take a look at these. Again, the mechanisms for some of these you're responsible for, some of them not as much, and those are things, again, that we would have looked at in Organic Chemistry 1. Let's move on from there and talk about functional group transformations. What does Luke say? I need to practice. You know what, Luke? Everybody needs to practice. Even this guy needs to practice. I've learned reactions in industry that I don't remember anymore. I developed reactions that I don't remember anymore. All right. In fact, I got an award, not many in my life, but I got an award once for developing a reaction, and I don't remember what it was. It was so long ago. Anyhow, let's get back to just functional group transformations. It says here, it's logical to review the two-step synthesis strategies from previous chapters, right? Moving a functional group from one carbon to the next. Here you see we move an alkyl halide, right? We move this bromine molecule, or this bromine atom, sorry. We do an elimination, and then we move it over to another carbon. Well, how would we do that? First, you'd have to do an elimination. And you'd have to eliminate the right proton, right? You can't just eliminate any damn proton there, right? There's a couple of options. You could eliminate this proton, right? That's a beta proton. Or you could eliminate this proton. And if you were to choose potassium Tbutoxide, you'd eliminate the proton highlighted in orange. But if you choose sodium methoxide, you're going to eliminate the proton highlighted in blue, which is the proton that you want to eliminate, right? And then from there, you're doing the Markovnikov Edition of Hbr across that double bond. And, you should all be able to, and sometimes I come off sounding mean, apparently. My students said, sometimes I sound harsh. I don't mean to. But anyhow, you should all know how to draw this mechanism, right? This is the carbon with the hydrogen, so the rich are going to get richer, right? You should be able to draw these curved arrows, be able to draw the intermediate carbocation that's formed. Let me draw that for you. It's a beautiful tertiary carbocation, right? And then the bromide that's left over is going to come in there. Right, it's going to do a nucleophilic attack like that. And there we go. So you should be able to draw that kind of mechanism. So there we go. What else? You should know how to do an anti-Markovnikov edition of Hbr across a double bond. We reviewed that. I talked about, using potassium Tbutoxide to make a Hoffman product. And you can see from this slide that we can take that bromine and we can put it on, virtually every carbon of that molecule, just using the reactions that we learned in Organic Chemistry 1. Very powerful stuff. Next year, functional group transformations, thinking about a hydroxyl that's highlighted in red here on the far left, right? Everybody knows what an alcohol is, but an alcohol is not a good leaving group. what if I wanted to do an elimination to make this alkene shown down here? Well, the first thing I'm going to have to do is I'm going to have to convert that alcohol into a good leaving group. And how do I do that? I use tosyl chloride, TSCl, and pyridine, right? And what that gives you, right, after that first step, you end up with this molecule. I'll just draw it here to help us out. You end up converting that into what's called a tosylate. A tosylate is a great leaving group. And what makes something a good leaving group? These are questions that you should be able to answer, because a good leaving group is simply the conjugate base of a strong acid. And I explained to you that toluene sulfonic acid, or tosic acid, is a strong acid. There we go. Then we have a Markovnikov addition of water to give us this tertiary alcohol. What else? Hey, there's one reaction on here that we didn't cover yet this morning. It's this one here. You guys remember this one here? Does anybody remember this reaction? Oxymercuration Demercuration. This is one of those reactions that I told you, you're not responsible for drawing this mechanism. I would never ask you to get a pencil and paper and just say, like, Taylor, sit down and draw me this entire mechanism. No, but I would expect you to understand the first step, why it works the way it does. And I'm not going to reteach that. But my question to you guys is, all that's happening here is I'm going from this alkene to this alcohol, right? This alcohol, and I'm using mercuric acetate and water followed by sodium borohydride. That, my friends, is just a Markovnikov addition. Can somebody tell me why the heck I would be using mercuric acetate? Why I would be messing around with mercury? What's so great about mercuric acetate? Who could tell me? Absolutely. Okay, so Diego and Andrew put in their answers, and they're both correct. Right? It's to avoid a carbocation rearrangement, right? Let's write it down here. Avoids carbocation rearrangement. Absolutely, absolutely. All right, let's move on to the next one. The next one's just showing the movement of a pi bond, changing its position. So here we start with 1-methylcyclohexene, molecule on the far left. Then we do a Markovnikov addition. So for that, we would just use Hbr. And then if I want to eliminate this proton, I'm going to use a big bulky base, right? I'm going to use potassium Tbutoxide, right? I'm going to use potassium Tbutoxide. Here's the Lewis structure of Tbutoxide, okay? And we're going to draw the curved arrows for that, right? This is just a plain old E2 mechanism, right? You extract a proton, make the double bond, loss of leaving group. There you have it, folks. You should be able to draw that mechanism. What else? So that's the reagents that are circled in red. Those are the ones that we looked at earlier. We also talked about Anti-Markovnikov addition, things like that. Look, this isn't something that Mr. Deon wrote, okay? This is something written by David Klein himself. I borrowed this from the master, okay? The author of our textbook. Says we have no chance to get this far unless we can easily recall all the possible reagents in reaction conditions first, okay? I'm a realistic person, Organic chemistry does involve some memorization. There's no doubt about it. There's no doubt about it. But as my brother said, my brother works in business and he has a chemistry degree, and he said, at least organic chemistry, it is logical. It's very logical. Anyhow, there we go. What else? Radical bromination. Right? If you're unsure about radical bromination, it might be a good idea to look at chapter 10, which deals exclusively with radicals. And of course, when you do the hydrogen abstraction to make the radical, you want to make the most stable radical. And so that would always brominate at the most stable position. So here we get a tertiary alkyl halide. And so for that, as Sean mentioned earlier, you would use bromine and white to do that. Then we eliminate to get the Zaitsev product. What else? Double bond to triple bond, single bond. This is something that we looked over in detail last semester. Well, with that in mind, why don't we just get to it? Why don't we just try some practice? Because let's face it, that's going to help you more than anything. So let's start with question 11.3a. Don't look at the solutions. Okay, just, you have to bang your head against the wall, so be it. Okay, so it says here, propose an efficient synthesis for each of the following transformations. We're starting with an alkene, and we're making an alkyne. Does anybody have any ideas about where we might start with this question? Anybody have any ideas where we might start here? Winona, I hope I'm pronouncing your name correctly. And I agree with you 100%, is to start by treating this with bromine. And I would kind of think about this reaction backwards, right? The only way that you guys know how to make an alkyne, right? There's no change in the carbon skeleton here. The only way that you know how to make a triple bond is from a geminal or a vicinal dihalide, right? And so if we treat this molecule with Br2, so I'm going to kind of be a little unorthodox here, but if we treat this with bromine, we end up with what? We end up with this molecule where we have a bromine here and we have a bromine here. So now we have a vicinal dibromide. And now we can take that vicinal dibromide and we can do a double elimination followed by deprotonation and then addition of water to make the terminal alkyne. So in order to do that, first we're going to treat it with excess sodium amide, and then in the second step, we're going to treat it with water. And that will give us the product, which is this product right here. Okay. All right. There we go. Let's take a look at the next one. The next one, we want to take this primary alkyl halide and we want to make a tertiary alkyl halide. Well, look, I like to think of this problem in terms of retrosynthesis, right? If you remember retrosynthesis, it's not synthesis with bell bottoms or lava lamps or anything like that. It's just going backwards and just saying, okay, well, what if I had this molecule? What if I had methylene cyclohexene? I could treat that with HBr, right? If I had that molecule, all I'd have to do is treat it with HBr, and I'd get a Markovnikov addition to make the primary alkyl halide. Can anybody tell me, is there a way to get from, now I'm kind of running out of colors here. Let's see. I'll use the orange. Is there a way to get from this primary alkyl halide all the way over here? Forgive me, these arrows are a little unorthodox, but is there a way to get from here to here? All I would have to do is eliminate this proton, right? Absolutely, David. Yes, I would treat that with a hindered base. Now, the reason I would use something like potassium Tbutoxide or DBU is to avoid any SN2, right? Because this is a primary alkyl halide. And so I want to avoid that SN2. So I'm going to choose the reagent that David gave me, which is potassium Tbutoxide. Right, so let's backtrack a little bit here. I'm going to get out the black pen. And so for the first sequence, right, the first step is bromine. The second step is excess sodium amide. The third step is to treat it with water. The second sequence, the first step is to treat it with potassium Tbutoxide. And the second step is to treat it with HBr like that. So the first one is a 3-step sequence, and question B is a 2-step sequence. There you have it. It's 9:08. Oh, we got lots of time. Let's. Who's enjoying this? Is anybody enjoying organic chemistry thus far? All right, Luke says me. Okay, I'll take that to the bank, Luke. That's got to be worth like a bonus point to be the first person to answer that. All right, hold on. I'm trying to give you the thumbs up. There we go. Oh, wow. Holy crap. I'll take all of this positive feedback. That's great. Oh, this is good. Okay, this is the kind of thing where it'd be a lot more fun in the classroom, because we can kind of gauge, you can kind of gauge where you are with your friends or whatever and say, hey, I'll take you up on that bonus point. Yeah. Okay, great. This is great. I'm glad that you guys remember a lot of these reactions. And remember, on Wednesday, virtually all we're going to do is practice, practice, practice for 75 minutes, okay? And we'll talk a little bit about respondus maybe for a second, okay? So let's just, concentrate on practice, practice, practice. You can never practice enough in organic chemistry. Let's try the next one, which is taking this, what's called exocyclic alkene, because the alkene is sticking out of a cyclic system, and then you have the internal alkene. Anyhow, does anybody have just any cool ideas about C they want to share with us? Anybody have a cool idea they might want to share? This one, or have an idea of where to start? Winona says HBr. I like the way you think. Yeah, if I was to take this molecule, and if I was to treat this with HBr, then I would get a Markovnikov addition, right? What would I get after the first step? I would end up with this molecule, right? Markovnikov addition. Can I take this molecule and can I make that alkene? Yes, absolutely. I would just treat it with sodium ethoxide to pull off the more hindered proton to make the Zaitsev product. And so the second step is going to be nothing more than sodium ethoxide. Right? These are all reagents that you've seen over and over and over in organic chemistry. HBr, sodium ethoxide, familiar players. Let's try one more quickly. The first one, look, if you were faced with this question, D, on an exam, look, if you have an alkane, you have methyl cyclopentane. There's literally nothing that you can do with that except burn it, which is never going to be the answer in this class. Or you can add bromine, right? So Br2 and light. And then in the second step, I'm going to treat that with sodium ethoxide, just like we did in the last problem. There you have it, folks. Perfecto. Now let me see here. Okay. I'm going to go back into my teams. And I'm going to see, for some reason, my camera is not working. I know you're really upset about that. And I don't know why it's doing that. Anyhow, all right. Does anybody have any questions? Anybody have any questions? Sorry, I'm trying to find the chat here. Yes, above. What's the question? Sorry. How do you know what the steps are for the reaction after HBr? Because you have to do if you're talking about question D, you have to do an elimination reaction, right? That's the only possibility there. So in D, right, you start with methyl cyclopentane, you brominate that, and you end up with a tertiary alkyl bromide, right? And if you want to make this compound, you have to do an elimination, right? That's an elimination reaction. And so you have to pull off this proton, the more hindered proton. Because if you were to use potassium Tbutoxide, you'd end up pulling off this proton and making this compound. That's not what you want. When you use sodium ethoxide, it's so small, right? It's not a bulky base. And so you end up removing this proton, loss of leaving group like that to make a double bond. Does that help, Luke? David says, are we doing any new mercuric acetate sodium borohydride reactions for the rest of the course? The answer is every reaction that you learn in Organic Chemistry 1 is you are responsible for in Organic Chemistry 2 and is fair game for Organic Chemistry 2. So the answer is yes. You will see that reaction come up again in this class. All right. Any other questions? So I forget who it was that was recording. I don't remember. Sorry. My memory's not that good. So whoever was recording, if you could stop the recording now and then share it with me, and then I will post it to Canvas for everybody to look at.